is what we are very certain of. Means for knowledge graphs. And next speaker is Robert Nilsson from Volvo Cars. Robert is a technical leader, model-based systems engineering at Volvo Cars. And you have been part of the joint working group since one meeting yesterday and today. Yeah. So you're next to present.
Yeah.
So here we go.
Thank you. So first, thank you for that introduction. And so let's kick off. I'll go through how we get to the means of digitalization at the end. The purpose of this presentation is not to explain the whole standard in 20 minutes. It's rather to give enough background, hopefully, to get an idea and a central line for the presentations today. And at the same time, also try to advocate why we think this standard is so good for particularly digitalization. So just to check, can you hear me well at the end? Raise up a bit. Yep, thank you. Mm-hmm. So with that said, then I'll start with the four main types of model type that are used in URMSM. And to be clear as a start, this is one interpretation. This is not the truth of the standard. Okay, so you could probably interpret some of the things that are shown here differently, and that will be okay. There are some conformance criteria. I will come to them later. Talking on a in this case with an OPM notation, it would say that the left, the blue type, unified reference model for smart manufacturing, is specialized into a smart manufacturing reference model, which in turn then is specialized into a smart manufacturing implementation, information model, which became a question. Is it implementation model? It's implementation model, right? Yeah. So I wrote wrong. It's smart manufacturing implementation model. I'm so into my information models, so I misspelled it. So now we know in this case. And then the trick is that it's not specialized again, but it's rather instantiated into a smart manufacturing system, which then becomes the representation of the knowledge that we wanted from start. And these are the main concepts that we will walk through. How do we get? And as Professor Kimura said, at the top two is a focus of the technical report that is ongoing right now, but we will talk about all four in the test cases today. So taking them piece by piece, not so much on the clicker.
It is not working.
Oh, okay, sorry. No? Yes. Now, the blue one then, Unified Reference Model for Smart Manufacturing, consists of two things. One is the dimension, which in turn consists of aspects. Okay, so that's the main part of that model type, which things that you need to define to be conformant with the standard. And once you have that, then you could go over to the other type. But before, you need to make sure that the criteria for conformance is met. And one of them is that you're using at least one dimension, which is called an essential type. And there are examples of essential that can be lifecycle management, for example. It's an essential dimension. And then you're free to invent other dimensions as well, according to your case. And the thing is also that aspects are organized under dimensions. So it's very strict ownership. And you need to show how these relate to each other. And that can be done explicitly in different ways. And the minimum is to show how concepts used by the aspects are related to each other. And that minimum is what we've been using so far in the work. So if we then focus on the smart manufacturing reference model, that's actually the model then defining the concepts, because in that you would show the relationship to the concept, but the concept repository, if you will, is actually defined on the other model type, right? So they become a dependence between them. I'll come back to that dependence later. But in big, then we have like a smart manufacturing reference model, which consists of a semi-formal ontology, which in that case means that you have defined a set of concepts uh, and also conceptual relationships. So basically, we have defined things and what things mean in relationship to each other. And then the standard stipulates that you need to go over another standard called 42010 to secure viewpoints. Or it's preferred that you go this standard because you need to secure viewpoints. And that particular standard is pointing at how you do that over a set of concerns and stakeholders and support. But the outcome and the most important thing is that the viewpoints then cover the concerns that stakeholders might have from different perspectives in context of the concepts so that they make sense for your aspects and dimensions. And that's actually one of the central things. And then, of course, your smart manufacturing viewpoints will relate to your semi-formal ontology because it's clarifying the context for it. And as I said, then the green ones can then form a concept repository. And the important thing is that the viewpoints are established. If we then look at what's in the smart manufacturing implementation model, it's actually then the information model consisting of information model elements. And I would say then there is a connection again then between the information model as a decided information model in relationship to the viewpoints that are established based on the concept repository. And this is quite important step for the work as such, because and also important to highlight the main difference because an information model is more formal. It has a set of rules that you decide. If you're used to work on UML or other similar notations, you would have cardinality, which basically means then you have one to many or one to one or many to many unpreferable modeling. But that's example of rules. You can also create other rules saying that this must be accompanied by this type or must not never be accompanied by another type or not allowed. And dependent on how you define those rules, the information that you will treat will give you different opportunity to work. There's a very important difference between setting the rules on the information objects and understanding the conceptual relationships in the concept repository. So in the green layer, we understand the world, which enables us to put rules in the yellow one so that we eventually then have a very clear structure, but also then can go into the smart manufacturing system where we have the instance. And if we look to the lower right, we would have the information element then, which is instantiated in the smart manufacturing system, which means that that's where it will happen. That's the actual data, if you like, in shape of information that is used in the practical sense of how you apply what you call smart manufacturing. And this is then this is the whole basic. And the smart manufacturing model type is then, of course, related to the tool meta model, because you are storing the data somewhere. And that data is then following the tool setup for how it's treated in the tool, which preferably is aligned with the rules of the information model and is actually using a set of symbols, and then they're then carrying the data, for instance. And that's the whole concept, basically, which the standard then is covering and which will be the background for today's discussion. And what's happening, I think that it's interesting to point out is that we basically have two kind of morphisms or changes, which shape changes, which I could call them sometimes, which are related and correspond to each other. And you can treat them differently, but you need to keep track of them. So if I have a set of dimensions which consist of aspects, they use words they use words and definitions as concepts. These concepts need to be defined and they need to have a meaning in relationship to each other. And that's where the first morphism kind of arises, because you need to track that a concept might be used for different reasons. Like the concept of friction, we can write it with a my, right? But the my can also be a micro as a prefix. It's the same symbol. It means totally different things, right? And the friction can still be conceptualized, and it's important to understand the concept of friction, because we can talk about the concept of a friction, for example. And if we studied in physics, we know what that means. But it might work differently in different contexts, dependent on the different material that have friction between them. So we might need to infer rules dependent on the context. And that's where we need to clarify the concepts of the friction to the domain where it's relevant to talk about the friction and the representations. So then the first thing we need to organize and understand how the concepts are shared between aspects, for example, so that we can know that we're talking about the same things. That's where we can align domains. If we come from different domains, we can align over dimensions and aspects that we share concepts. We are on this abstraction level talking about the same thing. We know that and we've secured that. Good. Let's keep track of that, and we can stipulate it mathematically, which actually means that we can track it in a big matrix. And that's the first level of morphism that can evolve. Second way is then that we put details on the conceptual relationships, creating information rules on the things. And that's the second level of morphism then that we expect when we go into the information. And then eventually that information is treated in a tool, which is instantiation. And that's the whole concept. And today we will present different test cases where we've tried this concept. And I won't go into details of them now. I'll just like to say that they are on different abstraction levels. So we'll talk about different things, but we will follow the same principle. Mm-hmm. And that's basically what I had to talk about for the introduction of URMSM.